Hello, welcome to another Stat 510 video. In this video, we're going to talk about simulation. So let's do that. So, what have we been doing in this course so far? So, re- after we sort of got through our review of probability, we sort of introduced the main task of this course, which is going to be statistical inference. So, long story short, we have some data. We want to sort of infer the distribution that generated the data. But often there are sort of subtasks along the way we want to do, say, estimating particular quantities, maybe estimating those quantities with an interval or performing a hypothesis test that will often involve uh, needing to estimate this f potentially, but also estimating other quantities. But just a recap of sort of where we are and what we had done, we said, okay, so how do we estimate f? And to be clear, we've only seen one way to do this, but the one way we've seen to do this is extremely general and pretty much always works. Works here is, it's a valid estimator. It might not be the best one, but it is an estimator that is reasonable. And that's by using the empirical distribution. And then sort of the next obvious follow-up question to that would be, well, maybe we're not interested in the distribution itself, but some property of that distribution, which we've been noting by T of f, which we've called a statistical functional. And the way we do that is, well, utilize the empirical distribution that we already have, and then something called the plugin principle to create a plugin estimator. So those are two sort of super generic techniques. One is for estimating a distribution, and then one is for estimating properties of said distribution. Now, when we do that second step and derive an estimator for some property of a distribution, what we're ultimately creating there is a statistic. So I'm going to sort of walk away from the plugin estimator now and just talk about a statistic in general. But so I'm going to use T sub n to denote some statistic, and it's some function of the data. Okay, so we're going to be interested in this statistic, and that could be a statistic derived via a plugin estimator or just any generic statistic. And something that we generally want to know when we have a statistic is its distribution, which is often called the sampling distribution. So here we have our usual setup. We have some statistic. And the natural question to ask is, well, what is the distribution of that statistic? And then there could be follow-up questions, which maybe beyond just the distribution, maybe we're interested in particular properties of the distribution. For example, maybe we're interested in the mean. Maybe we're interested in the variance, or any other reasonable thing. So that's what we want to be able to do. And I think what you'll find is that this is something we can do very easily sometimes, but other times this is a little bit more difficult. So for example, so here I have sort of the most common setup and the most common statistic. So here we have x1 through xn that are IID. That's what this notation sort of indicates. Normal random variables with mean mu and variance sigma squared. And then we'll look at our favorite statistic, the sample mean. So the question becomes then, well, what is the distribution of the sample mean? And in this case, we actually know exactly what that distribution is. That's not it though. Oops. Should be like this. There we go. So that is the distribution of the sample mean in this case. So here, deriving the distribution of the statistic is, I don't want to say trivial, but at this point in this class, you should know this fact. So this was easy. So, getting the mean of the statistic, getting the variance of the statistic, say, getting maybe something like a quantile. All these things are easy to do because we know the distribution of the statistic. Okay, great. Okay, so how about a harder example? And by hard, I mean one that I don't want to do. So here I sort of arbitrarily defined a random sample from an exponential distribution. I defined a statistic, which is the sample variance. And then my question is, what is the distribution of this thing? And I think what you'll find is, I'm guessing deriving this particular fact would not be too difficult and you could do it. Analytically, with nothing but probability theory, figuring out what this distribution would be, I'm sure there are smart people out there that can do it if it's possible in this case, but I myself am not good at these things. So in this case, I would sort of throw my hands up and go, I don't know. I don't want to do this. And this would be similar for other things too. Like if we looked at the median or a quantile or a bunch of other statistics under this setup or various other ones, I would just throw my hands in the air and go, I have no idea what the distribution of this thing is. Okay, so we want to solve that problem. We want a generic method that's going to allow us to get sampling distributions of statistics under basically any setup. I should say that the way I've written these two examples, I've sort of been leaving the parameters not defined, like they're placeholders, and like in this example, we get something that's still a function of them. What we're about to do, we're going to have to assume parameter values, but it's still very general. Anyway, sorry, that's probably a confusing point at this point. All right, so here is the idea. So what we're going to do is first simulate some data. So we're kind of still living in fantasy land here, which is we're sort of living in probability world where we know the true distribution. The next video is going to solve that problem. But in this video, we're more interested in just, again, even if we know the true distribution that the data is being generated from, it's still non-trivial to get the distribution of a follow-up statistic. So again, that's what we're trying to do here. Okay, so step one, generate some data. And I'm going to sort of put an asterisk here, and I'm going to down here say what that means, which is that asterisk sort of indicates magic. By that I mean this is something that statistical computing has sort of solved this problem, but we're not going to go down that rabbit hole of describing how to do that. But basically, I mean, if you mess around in R a little bit, you know that there's built-in functions that do this. But beyond that, the ability to properly randomly generate numbers, it's a non-trivial task, but it is solved. Long story short, it mostly involves first generating uniform random variables on 0, 1, which there are ways to do. But again, not going to get into that. That is going to have to be truly magic. And then the follow-up thing you would do is you would use an inverse probability transform to go from a probability of 0 to 1, kind of reverse engineering then a sample from a particular distribution. But again, we're just going to claim that's magic. If you're a student at the University of Illinois taking 510, this would be answered very specifically over many weeks, I think, in like 428 or 525 on the grad side. So we're just going to but books have been written about this. There's just one I happen to have on my shelf, but suffice to say, we can do this. All right, I said too much. Okay, step two, calculate the statistic on that data. Okay, so what we did was we generated data from a distribution and then calculated a statistic. So then what we're going to do is we're going to repeat that a bunch of times. we're going to repeat it b times, where b is eventually very, very large. But so then what we're essentially left with is a bunch of different observations of not the data, but the statistic that we're interested in. So the natural thing to do then would be say, well, I can keep generating values of the statistic that I'm interested in. Well, then use the empirical distribution. That's not how you spell that. This I can't write apparently. Um, so symbolically, what we're doing here is we're using the sampling distribution of the statistic to, and I'll say, estimate the true sampling distribution. Empirical distribution of the statistics, estimating the sampling distribution. Okay. Here's sort of a schematic that says exactly what I just said there, but more pictorially. So starting at the top and going sort of down the left-hand side first. So here we have our population distribution, or our data generating process. Population distribution. Okay, cool. And again, we're living in some sort of fantasy land where we know what this is. In practice, that's not going to be the case, but because it is, it's useful. And I should say that, the ability to do this is very useful for statistical research, whereas, before you go down the long road of doing a bunch of math to understand the distribution of your statistic, maybe do some simulations first before you then see if you're in the right ballpark about developing a useful statistic. Okay, so, all right, so what do? We take a random sample of size n from f. And again, remember, this is quote unquote magic, and it's kind of the secret sauce that makes this work, but we can do it. Okay, so what I'm denoting here by x superscript 1 with the parenthesis is sort of, this is a simulated data set, and it contains n observations. Okay, and then what we do is we say, okay, with that data that I simulated, apply the statistic to it to calculate the value of the statistic. So t superscript 1, that is essentially our first simulated value of the statistic. What am I calling this? Value of statistic on first simulated data set. Okay, so that's doing it once. So then you just repeat it a bunch of times. So I'm going to say repeat b times. Okay, and I should note that we're going to want b to be basically as large as we can go, right? So depending on the situation, you need more or less simulations. So we call sort of one path here a simulation, or a simulated value of the statistic. Okay, so hopefully intuitively this sort of makes sense, and we're going to look at some examples in a second. But first, a mention of why does this work? So recall, when we talked about the empirical distribution, we mentioned this theorem called the Glinvenko-Cantelli theorem. And basically what it says is that the largest difference between the empirical distribution and the true distribution conversion probability to 0. So you have these two distributions, and the x that supplies the largest difference between the two of them, that eventually vanishes. So that's great. So in our case, what we essentially have here is t1, t2, right? So these are from f sub tn. So what we essentially have are a bunch of random variables, because again, statistics are random variables, that were sampled from the sampling distribution. So the thing you have to realize is that while the way it's stated here, we're sort of sampling from the sampling distribution, but what you have to realize is that this, while it's not directly sampling from the sampling distribution, it's a valid way to produce samples from the sampling distribution, if that makes sense, right? So the sampling distribution depends on the underlying distribution. So it's okay that we did this, even though I'm now writing it like this. But then, so this empirical distribution here would be the empirical distribution of those statistics. And the thing that it's very, very, very similar to then is that thing that we don't know, which is the sampling distribution of the statistic. Okay, so that's kind of my quick hand-wavy explanation for why does simulation work? Well, because the empirical distribution, if you have a really, really, really large number of observations, gets closer and closer and closer to the true distribution. Okay, great. Okay, so pretty clearly, we're going to need a computer to do some of this. So how do you do this in R? So basically, there's two steps. First, you write a function. What that function does is it will generate data, and then calculate a statistic. And then you use the replicate function because you just want to repeat that process a bunch. And what we're going to do now is do this for these examples here. Okay, so yeah, let's do that. I actually don't know if I set this up totally perfectly because I'm gonna want to be able to reference these later. So we'll figure that out. Okay, cool. Right, so here's R. And let's maybe, oh, it doesn't let me, okay. Good enough, but let's maybe just make this bigger. Okay. Okay, so here I have 3 examples, and each I defined a data generating process, I defined a sample size, and I defined a statistic. Okay, so our first example is actually pretty silly because it's generating data from a normal. So I'm gonna maybe rewrite this. No, I don't have a good way to do this. Okay, we're just gonna have to deal with, oh, here's what we'll do. Here's what we'll do. Well, shoot. Okay, I'll just sort of write it down. So here's what we're gonna do. So that example said we wanted to generate samples from a normal distribution of size 20 with a mean of 3, and it's a variance of 4, so that would be a standard deviation of 2. So I can repeatedly sort of do that. So this is the magic step, right? So every time I run that piece of code, it generates 20 new observations from a normal distribution with the correct mean and standard deviation. So that's perfect. So I'm gonna probably maybe write this a little more verbose than I normally would. So it's really clear what's going on, but I think you might see some simplifications. So I can say data is that. Okay, and then so I can generate data and then calculate a statistic on it. In this case, the mean. Except I didn't run this. Okay, so now I can sort of repeatedly run that, right? So ultimately, this is what I want to do. I want to just do this over and over and over and over again. In comes writing a function. So I'm going to say sim and calculate. Well, here's what we'll do. We'll say sim normal calculate mean. Okay. So it's a function. And this is going to be a pretty specific function. It's only going to do one thing. So we could clearly make this fancy and say, like, put different sample sizes here, pass it here, put different means here, pass it here, but I don't care about that. Also, I don't really need to do this line here where I store it as data and then calculate it. I could just put this mean function around this, but I'm just trying to be a little verbose. Okay, so I now have this function, and now sim norm. Okay, so if I run that function, it does the two steps that matter, which is generate data, calculate statistic. So now I just need to do this a bunch of times. Okay, so enter the replicate function. Okay, so I want to replicate this, let's say 2,500 times. That's big enough in this case, probably. And this is the thing I want to replicate. And I always forget, I want to tell it the name of the function. Because yeah, if I put the parentheses there, that would be running it. So, and then I want to store this result. So I'll say sim norm mean. Okay. I don't know if that's the best name, but good enough. Okay, let's run this. Cool. All right, so now if we look at what's in here, no, I was wrong. I need to do this. Okay, now I say if we do what's in here. Okay, right. What happened there is, I don't want to explain right now. But no, you have to actually run the function, so that means parentheses here. Okay, so this is it. These are 2,500 simulated values of the sample mean when data is generated from a normal distribution, yada yada. Okay, so we can do a couple things now. I'm gonna move my camera up here. So for example, I could look at a histogram of those things. Sort of no surprise, it looks kind of normal. I like to fancy up my... Okay, and then one more thing that I'm gonna do is, we know the true sampling distribution here. It's not a mystery. So I'm gonna add it. So I do curve dnorm, because I want the density of a normal with a mean of 3 and a standard deviation of the square root of the original variance, which was 4, divided by the sample size, which was 20. And I think I need to do add is true, and we'll do color is red. Let me run all that. I think that's the right code, but you never know. Aha. Everything's right except the scale is wrong on the histogram. So if I do, that'll do it. So that'll change it from frequency to density. Hey, those look really good. I would note that so the histogram is sort of like a visual representation of the distribution of the statistic here. Again, the statistic here being the sample mean, and then putting that density over it. You can kind of say, oh, they match, but sometimes it's hard to understand how well that actually matches. So I'm gonna do this. I'm gonna use the ECDF function on the data. Here, the data here is the what we have here. So this ECDF function is useful for doing things with the empirical cumulative distribution function. Generally, I don't like using it because I like the flexibility of writing it myself. But in this particular case, it does one thing that I like, which is that it makes it very easy for me to obtain a plot of the empirical cumulative distribution function. And then what I'm going to do is, instead of adding a density, I'll add the true cumulative function. That is the true distribution function of our statistic. Hey, that looks really close. Actually, something we're gonna do real quick is here. Okay. So that should be a good example to show us that, like, hey, the simulation stuff works. But just real quick, I didn't try this, so this might go really poorly for me. So what I'm gonna do is I'm gonna quickly make 3 plots. Okay, bear with me. Okay, so I'm gonna do this 3 times. So, there's probably a better way to do this, but I'm doing it on the fly, so I want to do it quickly. So I'll do something like this, and then we'll do something like this. Okay, so what I want to do, what I'm trying to do here is I want to demonstrate that notion we said. Oh, here I can show it. Right here? No. Here. Okay. I want to sort of demonstrate this, which is to say that we need to use a lot of simulations because the more we use, the more that this applies. So what I've done is I've done the simulations with only 50 and then 500 and then 2500. So let's run those real quick. And then what I'm going to do is I'm going to make 3 of these plots and I'm going to add a grid because I like that. And again, there are better ways to do this, which have less copy pasting, less me randomly changing numbers, but for the sake of doing it on the fly, here we go. And then I want to put these all on the same mf row equals c 1 comma 3. Okay, cool. So if I run this, hopefully it's sort of clear. I mean, it's even with only 50, it's off, but it's close-ish. You can kind of better see that it's a step function because there's only 50 of them. But hopefully this demonstrates to you that more simulations mean that the empirical distribution of that statistic gets closer and closer and closer to the true. Okay. All right. So next example, I'm actually going to skip to the third one because I think this could be boring otherwise. Okay, so here what we want to do is generate, so we're interested in the statistic, the sample median. Okay, so we're going to use a sample size of 17 and data from an exponential distribution with a parameter of 3.1. Okay. So actually, I'm going to sort of steal my own code. No, I'm not. I want to write it from scratch. Okay, so first thing we want to do, REXP, what I say, 17, and so I specified beta, so this should be 1 divided by that, because this is not the rate parameter. This is the mean. We generally use lambda for the mean parameter. All right, 3.1. 3.1. Okay, so I can generate data. I can also... What I say when we're interested in the median, so we're looking at the sample median. Technically, there's many sample medians. I would note that if you look into the documentation here, there's a bunch of extra settings you can provide here for specific sample medians. Basically, like how it breaks ties and does things like that, you have to consider. But we're just arbitrarily calling whatever by default in R is with the median function as a sample median, but it's more complicated than that. Okay. So here what we're doing is we're simulating from an exponential and we're calculating the median. Okay. So I now more or less have a function that does that. Okay. Check on that function. It works. So now let's do it a bunch, replicate. We'll do, I don't know, 10,000 of these. I'm just picking arbitrarily big numbers. And following my naming convention, we'll call this sim exp median. Okay, cool. So now, oops. So here's a bunch of medians. All right. So I could do similar stuff, right? So I could plot a histogram of these things. Oh, I need to reset my plotting environment. Okay, so that is a visual representation of the empirical distribution of the medians here, which is a sort of an estimate of the true sampling distribution of the median under these circumstances. So I think you might notice that this is not normal, which is, I mentioned that because oftentimes, like, with a large enough sample, we know that a lot of statistics end up converting to normal. Clearly not the case here. This is a skewed distribution. I would also note that, like, we said that sometimes we'd be interested in, like, follow-up things about the distribution. So this is just the distribution. But what if we wanted an estimate, say, of the mean of the sampling distribution? Well, plug-in principle. There it is. What if we wanted variance? I would note that this variance function, it doesn't exist. Technically, I should be dividing by n, not n minus 1 like this function is, but you get the point, right? So yeah, so once we have this empirical distribution, like, we can then reapply the plug-in principle, and great, that works wonders. So yeah, hopefully this is a lot of words to say something that's pretty simple, but I wanted to walk through this process a couple times. Just this idea that this is a super generic process, and it's incredibly important to research statistics. So any methodological research in statistics, folks are doing this. So a methodology project in statistics is basically about coming up with a new statistic. And when you do that, you often need to show, well, this statistic is better than this other statistic. And to do that, it often involves a lot of mathematics that's incredibly difficult. So one of the first things you do is you start testing your method through this idea here, which is performing simulations. Because sort of the issue I mentioned here is that, so like this simulation study that we did here, it's only valid for a sample size of 20, a mean of 3, and a standard deviation of 2, right? But if we look back really early on to kind of my motivating examples, here we see that this derivation of a sampling distribution doesn't depend on specific parameter values, but sort of works analytically in general. So to perform simulation studies to sort of check how your statistic is doing, this also doesn't depend on the sample size. The different sample size, we know what happens to it. So to do what's quote unquote called a simulation study, you would need to try different values of n. You would try different values of the mean, try different values of standard deviation. So basically, you're just throwing computing power at your problem to sort of get a first idea of what's going on, or potentially using it just because you can't do the mathematics and this is the best thing you could do. But so, yeah, so again, I'm saying so much about this, even though it seems like such a simple idea, just because it's the heart and soul of what we do in statistics. Like, somewhere there is a graduate student in statistics running simulations right now. I'm sure of it. That's what they do. They code up simulations and they run them. That's a big part of their job. So if you ever find yourself doing that one day, this is something that you'll be doing. Okay, I've started to ramble though, so that means it's time to end this video. Okay, so as always, if you made it to the end of the video, good job, and I will see you in the next one.